In 1911, Rutherford published his planetary or nuclear model for atoms. He said that an atom has a nucleus that is very small, very heavy, and positively charged. That raised many new questions. For example, what is the structure of a nucleus? What is the connection between the nucleus and radioactivity? That was the beginning of nuclear physics, the study of atomic nucleus. We now know that a nucleus can be composed of protons and neutrons, which are called nucleons. A proton carries positive 1e of charge. A neutron carries no charge. A proton has almost the same mass as a neutron, although a neutron is very slightly, about 0.14% heavier. There are a few terms we use to describe a nucleus. Atomic number Z is the number of protons in the nucleus. Neutron number N is the number of neutrons in the nucleus. Mass number A is the number of nucleons in the nucleus. And A equals to Z plus N. Note that mass number is not the same as atomic mass. To specify a certain nucleus, we usually use this notation, XAZ, where X is the chemical symbol for the element, A is the mass number, and the Z is the atomic number. For example, Cu, that's for copper. A copper 6329 has 63 protons and neutrons together, 63 nucleons, 29 protons, and 63 minus 29, which is 34 neutrons. By the way, if a nucleus has 29 protons, it has to be a copper nucleus. Therefore, it is not really necessary to specify both copper and the atomic number 29. Just one of those two will suffice. The little u is unified atomic mass unit. Its definition is that a carbon-12 has a mass of 12.00000 U. So 1 U would equal to 1.66 times 10 to the negative 27th kilograms, which is also 931.5 mega eV over c squared. 1 U is very close to the mass of a proton and is very close to the mass of a neutron. By the way, you do not have to memorize those numbers for the atomic mass unit U. Binding energy or bond energy is the energy required to break a bond. Because of the attractive strong nuclear force, it takes a lot of work to break a nucleus into its composite particles. For example, it takes a lot of energy to break a helium-4 atom into its composite particles. 4 minus 2, 2 neutrons, plus 2 protons, and of course also 2 electrons. Since we have to add the binding energy in order to turn this helium atom into these particles, which side do you think has more mass, the whole atom or the separate composite particles? The composite particles have more mass, because we have to add energy which is equivalent to adding mass. In order to break the whole atom into these separate particles, the separate particles added together must have more mass. Because the helium-4 atom is the helium-4 nucleus plus the 2 electrons. So the helium-4 nucleus must have less mass than the nucleons combined. Because we always have to add binding energy in order to break a nucleus, that means the total mass of a nucleus is always less than the sum of the masses of its nucleons. The mass difference between the two would correspond to the nuclear binding energy. If the mass difference, or called mass defect, is delta M, the total binding energy for an atom or a nucleus would be delta M times c squared, because E equals to M times c squared. We can also divide this total binding energy by the number of nucleons to get the average binding energy per nucleon. It is meaningful to talk about binding energy per nucleon because it can tell us how stable a nucleus is. The higher the binding energy per nucleon, the more energy is required per nucleon to break the nucleus apart, which means the more stable the nucleus. For example, this is a graph of an average binding energy per nucleon versus the number of nucleons. The first peak over here is helium-42. This part tells us that nuclei smaller than helium-42 is very unstable. And in general, as the nucleus gets bigger, it gets more stable until it reaches iron-56. Iron-56 has the highest average binding energy per nucleon, so it is the most stable nucleus. That's why there is a lot of iron-56 in the universe. In general, beyond the iron-56, the bigger the nucleus, the less stable the nucleus.